Welcome to Diagonalization. Today we're going to talk about the definition of diagonalizable, when it's possible to diagonalize a matrix, and then on your own you can read about one application of diagonalization is to find powers of a matrix. So the definition is right here. A is diagonalizable if it's similar to a diagonal matrix. And that means it can be written like this, where P is invertible and D is diagonal. Now let me show you in this example a quick way to check if a matrix is diagonalizable given D and P. So if we want to show this matrix A is diagonalizable, option 1 would be to compute P inverse and then literally to check and see if this equation is true. So multiply P, D, P inverse and see if you get A. Now that's fine if P is 2 by 2, but what if P is 3 by 3? Finding the inverse isn't going to be so easy. So an easier way is to take this equation here, multiply both sides by P on the right. AP is PD, P inverse P. This gives us AP is PD I, because P inverse P is I, but DI is just I, so we get AP is PD. Okay, so that's what I did over here. I used option 2. I computed AP, and then I computed PD. Now, PD is super easy because look at what happens when I right multiply a matrix by a diagonal matrix. This column gets scaled by 5, and this column gets scaled by 4. So that's an easy multiplication to do. You can imagine if you left multiply by a diagonal matrix, well, maybe you can't imagine, but what will happen is it will scale the rows and not the columns. Okay, theorem 5. Don't worry, I'm going to combine all our big theorems towards the end here. A matrix is diagonalizable if and only if it has n linearly independent eigenvectors. And here's the process for diagonalizing. And I have a proof of that at the end. And I'm not going to read it because you can read, but I'm going to go through that process with you and using an example. So we want to diagonalize this matrix A. So step 1, we need to find the eigenvalues. So we're going to solve the characteristic equation. And I have that set up for us. Now remember, you're not allowed to do row reductions before you find eigenvalues. So what I'm going to do is cofactor expansion on the top column. So this is 2 minus lambda. I think I said column, but I meant row. Negative 1 squared. Subdeterminant 2 minus lambda, 1, 0, 1 minus lambda. Okay, that's 2 minus lambda. And then when I take this determinant, I get 2 minus lambda times 1 minus lambda. So all in all, I'll have 2 minus lambda squared times 1 minus lambda, and that equals 0. So my eigenvalues are lambda equals 2 and 1. All right, now I want to find a basis for each eigenspace. So just to remind us of the matrix A and what A minus lambda I is, I put that at the top here. So we want to find a basis for the null space of A minus lambda I for each lambda. So for lambda equals 2, I'm solving A minus 2I times x equals 0, and I do that by reducing the augmented matrix A minus 2I augmented with 0. Okay, and so what I do is I look up here at my A minus lambda I, and everywhere I see a lambda, I put in a 2. So that gives me 0, 0, 0, I'm augmenting, so 0 all across the top, and then 1, 0, 1, 0, and then negative 1, 0, negative 1, 0. Okay, and we're going to reduce that to reduced echelon form. That's pretty easy. Take the second row, kill the third row, and then take that second row and move it up to the top. So I'm only going to get one non-zero row, and literally everything else is zeros. All right, so x3 is free, that's t. x2 is s, that's also free. And x1 is negative t. So a basis for the eigenspace, which is automatically 2 linearly independent vectors. I'm going to put my t vector in first, negative 1, 0, 1. And then my s vector, 0, 1, 0. And I'm going to name these just for later use. This is p1. And this is P2. Okay, now I do the same thing for lambda equals 1. And I've already set up the matrix here. I've got A minus the identity augmented with 0, and I reduced to get this matrix here. I'm in reduced echelon. And so my x3 is, again, free. My x2 is negative t, if x3 is t, and x1 is 0. So a basis here just has one vector, 0, negative 1, 1. Let's call that P3. Now I'm going to form P and D. And this is the part where, let me scroll back here, the order must match the order of the entries in D. So P and D come in a pair, and you can put those vectors, the P vectors, in any order you want, as long as their corresponding eigenvalues go in the right place in D. So let me show you what I mean by that. Let's form the matrix P first. So I'm going to put in P1, P2, and P3. So negative 1, 0, 1, 0, 1, 0, 0, negative 1, 1. So I chose P1, P2, P3. Now P1 and P2 corresponded to the eigenvalue 2. So what that means is when I form D, which is a diagonal matrix, I need 2's in the first 2 slots. Now this is diagonal, so everything else is going to be 0. And then in this last entry here, I need the eigenvalue corresponding to P3, which was 1. And then I'm not going to do the safety check. AP is PD, but you could. Other options for P and D are over here. There's a bunch of them. Like, for example, suppose I wanted to put the 2's on either side of the 1 in my diagonal matrix D. That would be fine, but I would just need to make sure that that eigenvector corresponding to lambda equal 1 went in the middle of my P matrix. So you can read through those options there. Okay, so here's a short one. Here we've got a matrix A, and it's been diagonalized for us. It's written as PDP inverse. Find the eigenvalues of A and a basis for each eigenspace. Okay, well, the eigenvalues are sitting right here. All right, so we've got 2 eigenvalues, lambda equals 6 and lambda equals 5. Now, there are 2 eigenvectors corresponding to lambda equals 6. Now, since the 6's are in the first 2 columns of D, then these 2 vectors form a basis for the eigenspace corresponding to lambda equals 6. So we'd want negative 2, 0, 1, comma, 0, 1, 0. And for lambda equals 5, a basis for the eigenspace would just be that last column vector, negative 1, 2, 0. And in order to do this, answer this question, I didn't even need to know what P inverse was. Okay, conditions for diagonalizability. Recall that the algebraic multiplicity is the multiplicity as a root in the characteristic equation, and the geometric multiplicity is the dimension of the eigenspace. And we always have GM less than or equal to AM. So I've put together some theorems in your book as one big theorem just to make it easier for you. You've got an n by n matrix A. It's diagonalizable if and only if it has n linearly independent eigenvectors. That's theorem 7. Okay. It's diagonalizable if and only if the GM equals the AM for each eigenvalue. And then lastly, if A has n distinct eigenvalues, A is diagonalizable. Now, what's happening in this case, if A has n distinct eigenvalues, that means the AM is 1 for every eigenvalue, and so automatically the GM is equal to 1. The GM can't be 0. The smallest the GM can be is 1. And if the AM is 1 and the GM has to be less than the AM, less than or equal to, then in this case, each of them is 1. And that's not, and if and only if A doesn't have n distinct eigenvalues, it doesn't mean A is not diagonalizable. For example, up here, we only had 2 eigenvalues, 2 and 1, and yet our matrix was diagonalizable. And the reason was that the AM of lambda equals 2 was 2, but so was the GM because I had 2 vectors in my basis. Okay, just some short answer questions here. Explain why this matrix is diagonalizable. All right, hopefully you've thought about that for a second. First of all, it's a triangular matrix. It's lower triangular, so we can read the eigenvalues right off the diagonal. So we see we have 3 distinct eigenvalues. So that falls under C, this category. If we have n distinct eigenvalues, we're diagonalizable. All right, here's a slightly more complex one. Suppose you want to diagonalize a 4 by 4 and you're given the characteristic polynomial. What eigenspace are you going to find first? Remember, the characteristic polynomial is a characteristic equation without the equal 0. But if we imagine that equals 0, we can read the eigenvalues right off of that polynomial. So let me make a little chart here. We've got lambda, the AM, and the GM. Our eigenvalues are 1, -5, and 2. The AM of lambda equals 1 is the exponent there, that's a 1. And the AM of lambda equals -5, again, is a 1. And the AM of lambda equals 2 is a 2. GMs. Well, the GM has to be less than or equal to the AM, and you can't have a GM of 0. There's got to be at least one vector in your basis. So the GM here is going to have to be 1. The GM here is going to have to be 1. But in this last case, GM could be one of 2 things. It could be 1 or 2. So the one you want to check first, if you want to diagonalize, is this guy. You want to check the eigenspace for lambda equals 2 first. Here's why. If you find that the eigenspace for lambda equals 2 is one-dimensional, you can quit. You're not going to get enough linearly independent eigenvectors to diagonalize. You need 4 of them. So stop right there. Whereas if you were to compute this first and this first, you've done all that work just to get down here to this last case and find out, dope, A is not diagonalizable. So I would check this one first, and then if it's 1, you can stop. If it's 2, then you know A is diagonalizable, but you're still going to need to find bases for eigenspaces for these other 2 eigenvalues. Okay, one last thing here. Diagonalizability and invertibility are independent. So something I want you to think about, construct a 2 by 2 matrix that is invertible but not diagonalizable, and then turn it around and try and construct a 2 by 2 that's diagonalizable but not invertible. And I've got the answers on the next page, but give it some time and see what you can come up with and see why those hints might make sense. All right, and then what else do we have here? You can read this on your own, powers of a diagonal matrix and diagonalizable matrices, and then the proof of theorem 5. And that is the end of this section.